Good evening, class. We are looking at Chapter 2 review, limits and derivatives. Exam covers from 2.1 to 2.8, and now we are going to cover the synopsis of 2.4, the precise definition, 2.5, continuity, 2.6, limit at infinity, horizontal asymptotes. 2.4, the precise definition. The limit of f of x as x approaches 3 equals 5. What does it mean? It means f of x is close to 5, meaning the y coordinate, when x is close to 3. We can make the values of f of x within an arbitrary distance epsilon from 5 by restricting the values of x to be within a distance delta from 3, but x cannot be equal to 3. As we look at the graph along the x-axis, for example, we are coming close to number 3 from the left and right within the distance of delta, and along the y-axis, we are getting closer and closer to the y coordinate 5 from the bottom and the top within the distance of epsilon. So if 3 minus delta is less than x, less than 3 plus delta, where x can't be 3, then 5 minus epsilon is less than f of x, less than 5 plus epsilon. In other words, along the x-axis, within delta, along the y-axis, within epsilon, both of which are extremely small values, delta and epsilon. By taking the values of x not equal to 3 to lie in the interval of 3 minus delta and 3 plus delta, we can make the values of f of x lie in the interval of 5 minus epsilon and 5 plus epsilon. Precise definition of limits. Let f of x be a function defined on some open interval that contains a except possibly at a itself. We say the function has a limit at a, and we write the limit of f of x as x approaches a equals L. If for every small number, epsilon larger than 0, a positive value, there is a number delta larger than 0, again, very small, such that if the absolute value of x minus a, which refers to the distance from x, is between 0 and delta, so then the absolute value of f of x minus L is less than epsilon. So this is the distance of x from a, this is the distance of f of x from L when we put an absolute value. Now this entire thing can be put into this, which is red. This is red, whatever epsilon larger than 0, there exists a delta larger than 0, such that if the absolute value of x minus a is less than delta, then the absolute value of f of x minus L is less than epsilon. So it's this symbol in math, whatever, this symbol in math, there exists. And this line segment, this one means such that. And so what does this mean? Along the x-axis, somewhere between a minus delta and a plus delta, because we are approaching a in general. In this case, a is 3. And along the y-axis, we get somewhere between L minus epsilon and L plus epsilon, because this one in general is the limit of the function. So in essence, the limit of f of x as x approaches a equals L. So we are dealing with the following situation, the limit of f of x as x approaches a equals L. That's the meaning of it. All right. So that's a precise definition. It says use the graph to find delta such that if the absolute value of x minus 3, that means the distance some point x has from 3 is between 0 and delta, that gives us absolute value of f of x minus 2 is less than 0.5. And I like to write it in this fashion, which is the simplified version. Of course, if you look at the graph, the value of a is 3, and we are coming towards it from the left and right. The value of the limit is 2, and we are coming towards that from the bottom and the top. And in this situation, let's start with this expression. The absolute value of f of x minus L is less than epsilon. So you start with that, and you just write what's given. Of course, for this question, you don't even need that, but I want to give you the general way of writing this. As you recall, with the absolute value inequality, if absolute value of x is less than k, where k is positive, then x is sandwiched between minus k and positive k. So I hope everybody remembers that. And therefore, this one becomes f of x minus 2, because 0.5 is positive. We drop the absolute value, we put negative and positive, negative 0.5 and positive 0.5. And now we move negative 2 around, meaning we add 2 to all sides. And so f of x is between 1.5 and 2.5. We already have that from the graph, but even if we didn't have the graph, we could figure it out, okay? But here's the thing. We want to use the graph to find delta such that this works, okay? So what is delta? Delta is the distance from A. In this case, A is 3. The number of interest is 3. And so according to the graph, we go from somewhere between 2.6 to 3.8. And here's what we need to get. Take delta to be the minimum distance over here and here. In other words, 3 minus 2.6 is this distance. 3.8 minus 3 is this distance. We take the smaller of the two. Now, this distance obviously is 0.4. This distance is 0.8. And the smaller of the two is 0.4. And any smaller number than 0.4 will do. And of course, x can't be equal to 3. Now, the question is, why the minimum of the two? If you don't go with that, and you pick the one which is larger, this brings you further in. So just to see how that thing works, if I have 3 minus 0.8, it gives me to 2.2. So I can start somewhere here. Let's say it's 2.2. The problem is if you go up here and here, you will miss 1.5 to 2.5. The answer you get here is way off. So you must choose the smaller of the two. If you choose the larger one, it won't work. All right. Prove the limit of 4x minus 5 as x approaches 3 equals 7. And I hope everybody remembers we basically take the easy way out and we plug in and we observe. However, the precise definition says prove it, and I have this general statement here, and what it means is this. Guessing a value for delta given epsilon larger than 0, we need to find or guess delta greater than 0 such that if the absolute value of x minus a is between 0 and delta, then the absolute value of f of x minus l is less than epsilon. And please understand the absolute value of x minus a less than delta, that means the distance, the absolute value along the x-axis, the absolute value of f of x minus l less than epsilon, the distance along the y-axis. So what is the methodology to prove that? We start from here. And again, I'm going to read this for you. Whatever epsilon larger than 0, there exists delta larger than 0 such that if the absolute value of x minus a is less than delta, then the absolute value of f of x minus l is less than epsilon. So we start with the second part. Okay, so we write this. As we have it from here. And if we plug in a is 3, so if the absolute value of x minus 3 is less than sigma, so you less than delta, so you have to write this. A is general. And you are going to replace f of x with 4x minus 5 and the limit with 7. So first we do the writing. So we follow this, we do the writing. And now we start from this and we work our way to find a relationship between the two. That's all we have to do to, find for the first part, relationship between epsilon and delta. So we always start with this, which means in this case here, and that is 4x minus 5 minus 7, which makes it 4x minus 12, less than epsilon. So we started with this part, everybody. 4x minus 12, you can factor the 4 out and you can take it outside the absolute value. The absolute value of 4 is 4. If you divide both sides by 4, absolute value of x minus 3 becomes epsilon over 4, or epsilon divided by 4. Now you compare it to absolute value of x minus a less than delta. This part for this question is this. So let's put it down here. Compare it to this one. As you compare it to this one, you see the left side is identical. The right side tells us the choice would be that these two are equal. That would be the choice. So therefore, because of this, choose delta to be epsilon over 4, and it should work. That's really the bottom line. And that's the end of finding the relationship between the two. So the first half of this is to find the relationship in this statement between epsilon and delta. So delta must be 1/4 of epsilon. Now the proof is showing that this delta works. So basically you reverse the steps. So you start with this, and of course delta is epsilon over 4, or 1/4 of epsilon. So you start from this and you work your way back. Since this is epsilon over 4, let's multiply both sides by 4. we are interested in this part. So 4 times the absolute value of x minus 3 is less than 4 delta, which is equal to epsilon. So 4 times delta, 4 times that is epsilon. We can take the 4 inside, the absolute value becomes 4x minus 12 inside the absolute value. So we are reversing. And so we got, look at this one. We got this one. But we want this one. So just write minus 12 is minus 5 minus 7. Again, just look at your work. Trace it back. So make it look like that. 4x minus 5 minus 7 is less than epsilon. And now, when we combine these two, that gives us the expression here, and we write them together. If the absolute value of x minus 3 is less than sigma, less than delta, my apologies, then the absolute value of the parentheses for x minus 5 minus 7 must be less than epsilon. And now that's the proof that the limit of 4x minus 5 as x approaches 3 equals 7. And here's the graph. You have the function y equals 4x minus 5, which is a line. You choose number 3, and you get closer and closer to 3 from the left and right by a distance of delta that will take you to the y. 3 gives you exactly 7, and from the left and from the top and the bottom by a distance of epsilon. So 7 minus epsilon to 7 plus epsilon is the answer. And that takes care of the business. Continuity. A function has a limit at a if the limit of f of x as x approaches a from the left equals L and equals limit of f of x as x approaches a from the right. In other words, one-sided limits are identical. The limit of f of x as x approaches a equals L. Direct substitution property for polynomials or rational functions. If the function exists at the value a, then the limit of the function as x approaches c is equal to the function's value at a. That means the limit of f of x as x approaches a equals f of a. This is referring to functions being continuous at a. Class, every function we have discussed previously in algebra, in pre-calculus, every function is continuous in its entire domain. So, as long as you can write the interval of a function, then you're writing that it's continuous in that. For example, all linear, all polynomial functions have domain that would be all real numbers from negative to positive infinity. However, rational functions, you have to exclude what makes the denominator 0. So that's the concept that we are referring here. A function is continuous if the limit of f of x as x approaches a equals f of a. So that's the definition of it, continuity. A function is continuous from the right if the limit of f of x as x approaches a from the right is f of a, and a function is continuous from the left if the limit of f of x as x approaches a from the left equals f of a. Sometimes you're dealing with a function that is not continuous at a, but it could be continuous from the left or right. Okay, nevertheless, it doesn't make it continuous. It just makes it continuous from the left or right. Also, if we look at this one, it gives us the concept of what we call the intermediate value theorem, short IVT. If f of x is a continuous function on the closed interval of a to b, and we let n be any number between f of a and f of b, where the two values are not equal, there must exist a number c in a to b such that f of c equals n. So the bottom line is if you look at this function, there is no break, there is no discontinuity as we go from A to B. If you pick a value, if you draw a horizontal line that in essence gives you the value at that point, and because the function is continuous, and this has a value f of a less than this f of b, then there has to be at least one point somewhere in between a and b that the functional value between a and b give us n. In this case, happen to have 3 parts. That means f of c sub 1 equals f of c sub 2 equals f of c sub 3 equals n. That is called the intermediate value theorem. And sometimes we use that to find zeros of a function. Now, let's look at this example. Determine C such that P of X is continuous at X equals 5, reminding everybody CT is short for continuous, as the following definition, limit of f of X as X approaches A must be equal to f of A. So, as we look at this expression, we notice that P of X is a piecewise defined function. P of X is X squared minus 25 over X minus 5 for X large not equal to 5. Otherwise, it's C, which means right here, it's important to understand the meaning of this. This says this one or P of 5 equals C. This means the pair 5 comma C belongs to the function. Okay, that's the meaning of it. Now, because the limit has to be equal to the functional value, this is the functional value. What about the limit? You choose this one because when X is not equal to 5, you have this piece. You're going to take the limit of this function as X approaches 5. And you're going to work on that. If we plug in 5, we get 0 over 0. This is an indeterminate form. In the case of an indeterminate form, it simply means more work. Use your algebraic technique to fix the problem. The problem is the 0 in the denominator, not in the numerator. So you're hoping to get rid of that. Factoring is the technique that will do the job. And by the way, since X is approaching 5, you really should have a factor of X minus 5. You do have it in the denominator. Also in the numerator, everybody knows it's X minus 5, X plus 5, reminding you that A squared minus B squared is A minus B, A plus B. And 25 is 5 squared. So now we can get rid of X minus 5 and limit of X plus 5 as X approaches 5. If you plug in, you get. So we proved the limit exists and the limit from both sides is 10. And if we want it to be continuous, it must be equal to f of A, and f of a 5 is C. So the limit of P of X as X approaches 5 must be equal to P of 5, must be equal to C. So the choice for C must be 10. That's the only way that makes this piecewise defined function a continuous function. Show that the function is continuous on negative to positive infinity, where the function f of x is defined as a piecewise defined function sine x. if x is less than pi over 4, and cosine x if x is larger than or equal to pi over 4. Each piece, that means y equals sine x and y equals cosine x, those are trigonometric functions, and they are continuous from negative to positive infinity. Each piece, that means y equals sine x and y equals cosine x. None of them has any problem. And so according to this, and if that's the case, then it makes this one continuous from 0, from negative infinity to pi over 4, and makes the bottom one continuous from pi over 4. Power to infinity, which means the function f of x is continuous on the interval of negative infinity to pi over 4 union pi over 4 to infinity. But what about the endpoints, namely pi over 4? We have to check it out. And to check it out, we look at three things. We look at the limit from the left, the limit from the right, and the functional value. So to take the limit of f of x as x approaches a from the left, we're going to look at the limit of f of x as x approaches pi over 4 from the left. And for that, we are going to use less than. That means we are going to use the top piece. Plug in sine of pi over 4. We should know it's square root of 2 over 2. It's one of those common arcs. So the limit from the left is that, and now we're going to take the same limit, but this time as x approaches pi over 4 from the right, and because x is larger than pi over 4 here, we're going to use the second piece. So the limit of f of x as x approaches pi over 4 from the right is the limit of cosine x as x approaches pi over 4 from the right. And you plug in, as you know, cosine of pi over 4 is the same thing, square root of 2 over 2. So that means the limit of the function exists. Which is good so far. The next thing is to look at f of a. F of a, you look at the equality. So f of a pi over 4 is cosine of pi over 4, which is also square root of 2 over 2. This one says the limit exists. This one says the functional value is square root of 2 over 2. So the limit of f of x as x approaches pi over 4 equals f of pi over 4 equals square root of 2 over 2. Therefore, f is continuous at pi over 4. Because x is continuous at pi over 4, combining it with this, f is continuous from negative to positive infinity. So the answer to the question is yes. So again, each piece is continuous from negative to positive infinity. This one stops at pi over 4. This one starts with pi over 4. You look at one-sided limits, they're identical. You look at the functional value, you have to use the equality, everybody. And they are all identical. The limit is equal to the functional value. It makes it continuous at pi over 4. And we already proved it was continuous from negative to positive infinity, except at pi over 4 now. Everything is covered. At pi over 4, we did not know that. We had to check. Types of discontinuities. Here's f of x equals x squared minus x minus 2 over x minus 2. And here is the same function when x is not equal to 2 and 1 when x equals to 2. Parts A and C, these two parts, we are talking about removable discontinuities. That's the terminology. What type of discontinuity? Removable. Why is it removable? We could remove the discontinuity by redefining f of x at just the single point number 2. Look at number 2, we have a hole. The same thing here. The difference between these two is that at number 2, we don't have anything. At number 2, the functional value is given as 1. But the question is, why is this the case and what happens? Remember, when you graph a rational function, you set the denominator equal to 0 and you say that's VA. But before you do that, you have to make sure there is no common factor between the top and the bottom. This one can be factored into x minus 2 times x plus 1. X minus 2 drops, and this becomes x plus 1 when x is not equal to 2. So this one, g of x equals x plus 1, is the line with no hole. The line with no hole is this function. The line with the hole is this function. So the difference between these two is just 1 point. So this function is continuous from negative to positive infinity. If you look at this one, the functional value f of 2 is defined as 1. According to this, it's defined f of 2 equals 1, but you will have to redefine it to cover the point. If you plug in the 2 here, you get 3, which gives you the coordinates of the hole 2, comma 3. And so if you change this to 3, you fix the problem. That's why it's called the removable. Okay, so if you change the 1 to number 3, you cover the hole. That's how you redefine it. So you can fix it. On the other hand, if you look at these two cases, part B is called infinite discontinuity, also known as VA, vertical asymptote. You're looking at the function f of x equals 1 over x squared. If x is not equal to 0 and 1 when x is 0, that means the pair 0, comma 1 is part of the graph. There is nothing you can do to fix it. This one is called the jump. This is the greatest integer function. And there are, in fact, infinitely many jumps, and there is nothing we can do to fix it. So the only one that is removable are those two. In short, I hope you recognize the limit exists as x approaches 2. Now the functional value may or may not be there. This doesn't have a functional value, this does. If you redefine it, you fix it. But this too, the limit doesn't exist and there is nothing you can do to fix it. If the limit doesn't exist, it's not fixable. All right, reminding you that the limit of f of x as x approaches a equals f of a means continuity, and one-sided limit says if the limit of f of x as x approaches a from the left and a from the right are the same, the limit exists. So for this graph, at what point or points is f of x discontinuous? Name the discontinuity. If removable, how would you redefine to remove it? So let's look at the graph. And we can clearly see there is a hole here, there's a discontinuity here. There's a so this is -2. Discontinuity here, okay, -0.5. Discontinuity here, 0. Discontinuity here, 1. Discontinuity here, 3, 5. Now let's name each one. Clearly, if you look at 0, it jumps from 3 to 5, and from 1, also you see that it jumps from 0 to 4 at 1. So 0 and 1. At 0, we have a jump. At 1, we have a jump. Okay, everybody? So that's that. At 3, we have infinite, also called VA, vertical asymptote. The rest of it, -2, -0.5, and +5 are removable. Let's see how we can fix that. So if you look at -2 coming from the, we have to redefine it. So coming from the left and right of the first number, -2, here, from the left we are moving here, from the right we are moving here, and so we are moving towards this hole, which has a y coordinate 2. All we have to do, f of -2 equals to 2, and this discontinuity is fixed. As you can see, between -1 and 0, this is -0.5. So you approach it from the left and right. From the left, you're moving this way. From the right, you're moving towards the same point. And this point, what is the y coordinate of that? 3.5. So you redefine f of -0.5 as 3.5. What about 5? From the left, we move in this direction. From the right, this direction, left and right. In both cases, along the curve, we are moving towards this hole. And this hole has a y coordinate 5. So if we redefine it as f of 5 equals 5, we fix the problem. All right, the next example, use the IVT, intermediate value theorem, to show that there is a root for this equation, sine x equals x squared minus x between 1 and 3. And I've already discussed the concept of the intermediate value theorem. If f of x is a continuous function on the closed interval of a to b, and let n be any number between the two values, f of a and f of b, where the two values are not equal, and that's the key, there must exist a number c in the open interval of a to b such that f of c equals n. So you bring everything to the same side, and it doesn't matter, you take this to the right or this one to the left, and you set it equal to 0, and call this, so we took everything to the right, and call this something. For example, let's call it f of x. Now f of x, x squared minus x minus sine x, is continuous. Why is that? Because this part is a polynomial. This is a poly of degree 2. And this is a sinusoidal function. Both of them are continuous from negative to positive infinity. It's a combination of two, sum of two. The difference is also, remember, when you subtract, is a form of addition. So it's sum of polynomial functions and sinusoidal functions. So it's continuous from negative to positive infinity. So it is continuous. So the first thing works. The next thing is a closed interval. It's given to us a closed interval. So we are looking at a point in between. And sometimes, class, when you plug in, the endpoints don't work. So you have to go inside and find other numbers. But this one, simply by inspection, we are going to look at f of 1. And f of 1 is less than 0. Here's the reason. Let me erase this so you can see that. 1 squared minus 1 minus sine 1. Now, as you can see, these two cancel each other. They are both 1. Now, sine 1 is 1 radian. It's about 57 degrees, which is positive. Negative makes it negative, and that's less than 0. Okay, everybody? This is negative. Let's plug in number 3. And f of 3 is positive. Let's check it out. Plug in number 3 and observe. When we do that, we get 3 squared, which is 9, minus 3, which is 6. And why is this expression positive? Because sine, remember, sine of theta is between -1 and 1. So worst case scenario, this becomes 1, 6 minus 1 is 5. So f of 1 is negative, f of 3 is positive, 0 is a number between the two, IVT applies, and f of x is continuous from negative to positive infinity, also continuous from 1 to 3, and has a root in between. So a quick recap. First, we mentioned that this is continuous from negative infinity to positive infinity because it's a combination of a polynomial and sinusoidal function, which makes it continuous in the given interval of 1 to 3. Then f of 1 happened to be negative, f of 3 is positive, and the IVT applies, and it must have a root. And when we say it has a root, it may have even more than 1, but at least 1 root. Limits of functions at infinity. Here's the summary definition. Horizontal asymptotes HA of the curve y equals f of x is y equals L if the limit of f of x as x approaches negative infinity is L, or the limit of f of x as x approaches positive infinity is L. If you look at this case, the limit of 1 over x as x approaches infinity is 0. In fact, the limit of 1 over x to the power of p as x approaches infinity is 0 if p is positive. And that is the definition of a horizontal asymptote as an example. Also, the concept of limits at infinity. Let's look at a few functions. This is an exponential function where the base is larger than 1. This, or exponential growth. This is a function with the base between 0 and 1, y equals b to the power of x. It's an exponential function that it's an exponential decay. So, as you can see from the graph, the limit of, for example, e to the power of x as x approaches minus infinity is 0, which gives rise to the horizontal asymptote, and the limit of f of x as x approaches infinity is infinity. For the exponential decay, the limit of e to the power of minus x, as an example, as x approaches infinity is 0, and that means right here, horizontal asymptote for both cases has the equation y equals 0. That's the definition of the HA. And the limit of f of x as x approaches minus infinity is infinity. It blows up to infinity. And another example, y equals x cubed. As you recall, the limit of f of x as x approaches minus infinity is minus infinity. And the limit of f of x as x approaches infinity is infinity. If you remember, this was known as the end behavior in algebra. So when we wanted to graph functions, we needed to know the end behavior. For the function y equals x cubed, The end behavior takes us to the first and the third quadrant as an example, and it's truly helpful when we want to graph functions. VA, infinite limits, vertical asymptotes, VA, and we have the following situation. X equals A represents a vertical asymptote if the limit of f of x as x approaches A, or A from the left or A from the right, is either positive or negative infinity. If you look at this example, you know this is the function y equals ln x with the domain from 0 to infinity. And if you look at the concept, the limit of ln x as x approaches 0 from the right is negative infinity. And that means the VA has the equation x equals 0. Again, reminding you of functions you've seen. So definition of a vertical asymptote is given here, and here's the synopsis of that. The limit of f of x as x approaches A is positive or negative infinity, or as A approaches negative, A from the left plus or negative infinity, or the limit of f of x as x approaches A from the right plus or minus infinity. Another function that is familiar is tan x. The limit of tan x as x approaches negative power 2 from the left is minus infinity. Remember, it has the basic one. When we want to graph one cycle, we graph from x equals negative power 2 to x equals pi over 2. And this makes the VA x equals minus pi over 2. On the other hand, the limit of tan x as x approaches pi over 2 from the right is infinity. And that makes x equals pi over 2 another vertical asymptote. For its inverse, tan inverse, here's the function y equals tan inverse. The limit of tan inverse of x as x approaches minus infinity is minus pi over 2. And the limit of tan inverse of x as x approaches infinity is pi over 2. And that gives us the horizontal asymptotes. Okay. One of them is y equals pi over 2. One of them is y equals negative pi over 2. Now, let's see how we deal with the limits in general. When we want to do it algebraically, everybody. To find the limit, just plug in and observe. Limit of f of x as x approaches 8 gives you a number, you're done. Limit of function as x approaches 8 gives you 0 over a number is 0, and you're done. If the limit gives you a number over 0, just you have to figure out is positive or negative infinity. But in most cases, we end up with indeterminate form like 0 over 0, infinity over infinity, infinity minus infinity, 1 to the power of infinity, and things of that nature, which means more work, which means you have to use your algebraic techniques to handle the problem. So if you have a rational function or even a fractional format, rational function or a fractional format, so this is a rational function. And the variable doesn't matter, it's txn, is approaching infinity. The technique is to divide by highest degree term in the denominator. So it's t squared. The reason why is very simple. If you plug in, you get infinity over infinity. So that's the technique. We divide every term by t squared, everybody. And we simplify. So what happens is that this one, this one, this one, and this one. All of them have t or t squared in the denominator. And when you have any number divided by a huge number, it tends 0. And so you're looking at 0 over 1, which is 0. And it's important to understand you really have to write 0 over 1 before you get to 0, because if it happened to be 0 over 0, is also indeterminate. We look at this question, the limit of t squared plus 2t plus 7 over 5t plus 7 as t approaches infinity. Again, you're dealing with a rational function. And again, t is approaching infinity. And you have to divide by highest degree term in the denominator. This time is t. And again, if you plug in, you get infinity over infinity. So let's divide the top and the bottom by t. And let's simplify. So again, these two pieces, each one has a denominator which is infinity. They go to 0. Let's replace the t with infinity. In the numerator, you have infinity plus 2. And infinity plus 2 or minus 2 or plus 10,000 or minus 10,000 makes no difference. It's infinity. And if you divide infinity by 5 or 5 billion, it is still infinity. It makes no difference. Infinity is a constant. And what about this? If you plug in, you get square root of infinity squared plus 1, which is infinity, and then infinity minus infinity. And that is also indeterminate. So the question is, what is the technique? The technique is to multiply by the conjugate, and the conjugate of a minus b is a plus b. And the conjugate for this expression is the same thing, but with the plus. So we are going to multiply and divide by it, because this is equal to 1. You can only multiply by 1. How do you handle it? Extend the fraction bar and multiply these two, and recall a minus b times a plus b is a squared minus b squared. And so when we multiply these two, we get square root of x squared plus 1 squared minus x squared. This one comes out, and now x squared and minus x squared cancel each other. And now if you plug in infinity, the bottom is infinity plus infinity, and 1 over that is 0. So, to recap, when you have a rational expression and t is approaching infinity, the technique is to divide by highest degree term in the denominator. When you have a square root and you get infinity minus infinity, the technique is to multiply and divide by its conjugate. A minus b and a plus b are considered conjugate. What about here? Just plug in. E to the power of minus infinity is 0, and here's the reason. A to the power of minus m is 1 over a to the power of m. So e to the power minus t is 1 over e to the power of t, which means 1 over e to the power of infinity for this case means 1 over e to the power of infinity, which means 1 over infinity, which means 0. So the answer is 12 over 4 or 3. What about this one? T is approaching infinity, so does e to the power of infinity. If you plug in, you do get infinity over negative infinity. What is the technique? Similar to rational functions. When you have a rational function or a fractional expression where t is approaching infinity, the variable, then the technique for rational function is to divide by highest degree in the denominator. Now we divide by highest value. You can't say highest degree because they are transcendental functions. And so you divide by e to the power of t. You divide every piece, algebraic piece, and simplify. This remains, this becomes 1, this becomes -3. And because t goes to infinity, so does e to the power of t. It's important to know that, again, if t goes to infinity, everybody, that means e to the power of t goes to infinity, okay? And so with that being the case, this is 0, positive 1 over -3 gives us -1/3. Limit of x squared minus x as x approaches infinity. If you plug in, this is infinity squared, which is infinity minus infinity, and it's an indeterminate form. Technique, factoring. So let's factor the x out. And we get the limit of x times x minus 1. If I plug in now, I get infinity times infinity minus 1. And again, infinity minus 1 or minus 1 billion makes no difference. It's infinity. Their product is infinity. Infinity times a number divided by a number, they're all infinity. The only thing is you want to be careful with the sign. So as we look at this case, this is a rational expression. Because it's a rational expression, and because x is approaching infinity, and by the way, if you plug in, you get infinity over negative infinity. The technique is to divide by highest degree term in the denominator, namely x. So divide everything by x. So this gives you x, this gives you 1, this gives you 3 over x, this gives you -1, and this is what we have. If you plug in, you get infinity plus 1 here. Over here, you get 0 minus 1. And here's what's interesting. The numerator is infinity. The denominator is a negative value. That makes it a negative infinity. And that's the only thing you want to be careful of. Find the limits, part A, limit of e to the power minus x plus 2 cosine 3x as x approaches infinity. We use the limit laws and cut this into 2 pieces. The limit of this piece plus 2 times the limit of cosine. We get the limit of e to the power minus x as x approaches infinity plus 2 times the limit of cosine 3x as x approaches infinity, and it does not exist. Why is that? Let's see what happens. I hope everybody can recognize this one as 0 because you have e to the power of minus x, which is 1 over e to the power of x. And if you replace the x with infinity, you get 1 over infinity, which is 0. But what happens to cosine is what happens to all sinusoidal functions. The limit of cosine of ax as x approaches infinity doesn't exist. The limit of sine ax as x approaches infinity does not exist because they oscillate between -1 and 1. Remember the sinusoidal graph. So they oscillate between -1 and 1. So as x goes to infinity, the limit of cosine or sine fades. What about this case? We want to find the limit of e to the power of 3x minus e to the power minus 3x over e to the power of 3x plus e to the power minus 3x as x approaches infinity. And I hope you recognize the answer is infinity over infinity if you plug in, because e to the power of 3 times infinity is infinity. So is this one. And minus 3 times infinity, that means divide by it. And this goes to 0, this goes to 0. So you're dealing with a fractional expression. X is approaching infinity. The technique is to divide by highest value in the denominator, which is e to the power of 3x. So we are going to divide everything by e to the power of 3x. Let's see what happens. If you multiply this one by this one, you get 1. This one by this one, you get this one. What about this 2? E to the power of minus 3x divided by e to the power of 3x is e to the power of minus 6x. Why is that? A couple of ways to look at it. A to the power of negative is 1 over a to the power of positive. A to the power of m over a to the power of m, n is a to the power of m minus n. So if I look at just this one, just to clarify this one, you are going to divide this one by that. So e to the power of minus 3x divided by e to the power of 3x, according to this exponential, is e to the power of minus 3x minus 3x, and that gives us e to the power of minus 6x. And that's the same thing for this piece in the denominator. And of course, as x approaches infinity, e to the power of negative 6x goes to 0. So does this one. And the answer is 1 over 1. I hope you see there are a lot of things that come together here, the prior knowledge of mathematics and what we have learned before, for example, exponential rules. All right, let's move on. Find the limits. The limit of tan inverse of ln x as x approaches 0 from the right. And knowing the elementary functions and their graphs is truly helpful to find the answer here. So I'm reminding you that first, the limit laws indicate that we can take the limit as x approaches 0 from the right of ln x and bring tan inverse out. That's another way of approaching it because you're dealing with a continuous function. Now, what is ln x? ln x looks like that. And I hope you see from the graph that the limit of ln x as x approaches 0 from the right is negative infinity. I hope you remember when we discussed the VA, vertical asymptotes, and we looked at ln x. I reminded you of that. And so therefore, the limit of ln x as 0 approaches from the right takes us down to negative infinity. Also, the information about tan and tan inverse. Here's the function of a tan, y equals tan x. One cycle goes from negative power 2 to power 2. Those are the vertical asymptotes. For its inverse, and again, you can go back a minute ago, we went over that. We have two horizontal asymptotes, okay? One of them is y equals power 2. The other one is y equals negative power 2. So as we approach negative infinity, there seems to be a y equals minus power 2, which is the answer. So tan inverse of negative infinity is the answer, which is negative I over 2. So graphing and remembering elementary functions will help us find the answer. What is the limit of sine squared over x squared plus 1 as x approaches infinity? Now, anytime you have functions like sinusoidal functions, it's not going to be just plug in and observe, but rather we are remembering the squeeze theorem that says if f of x is less than or equal to g of x less than is or equal to h of x, that means g is sandwiched between f and h function. When x is near a, x possibly at a, and the limit of the left one, limit of f of x as x approaches a, equals limit of the right function, limit of h of x as x approaches a, and both of them are n, then the middle one that is squeezed in between, the limit of g of x as x approaches a equals l. So we are going to work on this. And remember, I told you the technique. Anytime you have a situation involving sine or cosine, remember sine or cosine is between negative and positive. If you square that, it's important to understand that this, of course, becomes 1. This really, not that negative 1 becomes 0. But if you have a negative number, any number, if you have negative 3, okay, and then some function, and you have positive 5, this goes to 25, you square it, but you can't square this and say 9, but rather it's 0, okay? Because any number between 0 and negative 3 will give you positive. Any number between 0 and 5 gives you positive. So it's from 0 to 25. In this case, from 0 to 1. We wanted to make it look like that. I hope you recognize if we multiply by 1 over x squared plus 1, we get this expression. If I multiply, the left side remains as 0, the right side is going to be 1 over x squared plus 1, and the middle is what we are looking for. This looks like the function we are interested in. So we are going to take a limit of this as x approaches infinity and this one. Obviously, both of them give you 0. The limit of 0 as x approaches any number is 0. And this one, when x goes to infinity, 1 over infinity is 0. Because both of them give us the same answer, 0, the middle one should give us the same answer by the squeeze theorem. Therefore, the limit of sine squared x over x squared plus 1 as x approaches infinity must be 0 by squeeze theorem. Find asymptotes where f of x is 2x squared plus 1 over 3x squared plus 2x minus 1. To find horizontal asymptotes, we want to find the limit of f of x as x approaches either positive or negative infinity, and they work in the same manner. Because this is a rational function, and because x approaches either infinity or negative infinity, you divide by highest degree term in the denominator, namely x squared. So let's divide the top and the bottom by x squared. So what do we get? We get 2 here. We get 1 over x squared here, 3, 2 over x minus 1 over x squared. And as you can see, since x is approaching infinity or negative infinity, this goes to 0, this goes to 0, this goes to 0. The answer is 2/3, which means horizontal asymptote has the equation y equals 2/3. Also, I'm going to remind you what we discussed in pre-calculus, and that is, if you have a rational function and you want to find horizontal asymptotes, if they have the same degree, then the answer would be just 2/3, y equals 2/3, just the coefficient of x squared, the highest degree term over the coefficient of highest degree term in the denominator. The reason behind it is exactly what we have shown here, because when You look at the horizontal asymptote, you're interested to know what happens at as x goes to infinity or negative infinity. And the values for 1 or 2 times x or minus 1 compared to these two become nothing, and therefore these two pieces, the leading term from the top and the bottom, they take over. So in essence becomes 2x squared over 3x squared. In other words, ultimately when x approaches negative or positive infinity, that's what happens. As far as the VA is concerned, and again, I'm reminding you of these definitions for horizontal asymptote, for vertical asymptotes. So what happens is that the VA, you can go through the process of taking the limit, or simply remember that you set the denominator equal to 0. 3x squared plus 2x minus 1 equal to 0. And it's an easy factoring because 3 is a prime number, everybody. So 1 and 3. And negative 1, you have no choice but to go with 1 positive and 1 negative. So it's a trial and error. It will do the job. We get the following. This gives us x equals 1/3. This gives us x equals negative 1. And those are the equation of a vertical asymptote. And again, for the factoring by trial and error, you would say x and 3x, and you put the 1 here, positive 1, negative 1, or negative 1, positive 1, and see which one works. As long as the middle term, take a look at the middle term here, minus x plus 3x, they must add up to the middle term 2x, and they do. Find a formula for a function that has VA x equals 1 and x equals 3, horizontal asymptote y equals 1. The reason it's asking for a formula because there are different ways of getting the answers. And so, for example, because we have this information, the solution, one possibility is the following. X equals 1, so you need x minus 1 in the denominator. X equals 3, you need x minus 3 in the denominator. Horizontal asymptote y equals 1. Notice the denominator, if you multiply, becomes x squared, and the rest is not important. It's the leading term that matters. And if you want to have a horizontal asymptote to be 1, the degree of the numerator must be identical, so it must be x squared. And the coefficient must be that the ratio is 1, so you have to have 1x squared. So this is one possibility, and one might say, okay, can you think of another one? And for example, if I add a number, any number, you make up any number, 5 or 3x minus 1, I still have the same vertical asymptotes and the same horizontal asymptote. And this is one possibility, everybody.